Hey guys, this is your Unit 7 study guide helpful hint video here. So I'm going to go ahead and go through the odd problems. I won't have time to go through all of them today. So let's begin. So the first problem we're looking at is a reducing problem or a simplifying problem. Basically what we need to do is we need to reduce. So we're going to reduce the numbers like we normally would. I know 7 goes into 14 twice, and it goes into 8. It goes into 56 8 times. I also see I didn't reduce enough actually. 2 and 8 can be reduced even more. If I divide the top by 2, I get 1. If I divide the bottom by 2, I get 4. So there's that. But we also need to reduce the variables. And when you have variables, basically, you're just going to subtract them. 2 take away 1 is 1. So I'm going to end up with an x to the first power, and it's going to go on the bottom because the bigger one was on the bottom. A good way to illustrate that is because x over x squared looks like this, and so when you reduce it, you're left with the x on the bottom, right? So wherever the bigger one is, that's where the leftovers go. But in any event, that's your answer for number 1. Number 2 is just an extra practice problem for you. I will show you the answer if you're interested, and there it is. But I'm not going to go over the evens, just the ones that I assigned you. Okay, as for number 3, it's another reducing problem, but this time we're looking at polynomials. And so when you want to reduce a polynomial, basically you have to factor them first. So I'm going to start by looking for a GCF. I do not see one. The next thing I'm going to do is I'm going to do the box method to factor it.
What the hell?
Hopefully it's 9 and 6. Let's try that. 12 and 9 do make negative 21 if they're both negative. So we have 2n minus 9 and n minus 6. I'm going to do the same thing on the bottom, but before I begin, I see that this one does have a GCF. I can take out a negative 7. So now I'm going to do the box on what's left.
I cannot wait.
And those make negative 7. So n minus 6 and n minus 1. All right. So to reduce this thing, basically all we do is cross that off. And we're good to go. That's all you need to do. As for number 4, this is just another reducing problem of the same nature, but if you want to see the answer, that's what you should end up with. All right. On number 5, I believe they're asking us to state the excluded values. Let me make sure. Look at the directions here. Yeah, number 5, we're going to state the excluded values. We talked about that, but I didn't quite use that language in class, so I'll explain what that means now. An excluded value is what I called an extraneous solution. In other words, it's what the denominator cannot equal. Now, the way that you find what r cannot equal is you take the denominator and you set it equal to 0. Or you could factor it to do it as well. This one's pretty easy just to solve, though. So r cannot equal 5/3 because the denominator cannot equal 0. Okay, so that's what we call an excluded value. It would also be considered to be an extraneous solution. I'll go ahead and do one more like this. Same question, find the excluded values. I know I wasn't going to do the even ones, but I'll do one more like this just for the sake of practice if you guys need it. So in this case, to state the excluded values, the denominator cannot equal 0. So let's set it equal to 0 first. Excuse me, getting over a cold here. We're going to factor it. And then we're going to do zero product property to solve. So there are two values that v cannot equal. It can't equal 3 and it can't equal 6, and that's because the denominator can't equal 0. So these would be your excluded values or your extraneous solutions. Okay? All right. On number 7, we're moving on into multiplication. Multiplication is a lot like simplifying. So the first thing you're going to do is you're going to factor anything that you can. On the top here, I've got a GCF. I can take out a 7p. And whatever you have on the top that's also on the bottom can go away. So the 7p's can go away. Multiplying anything by 1 doesn't change, so we can pretty much just ignore the 1, and we leave p minus 8 on top, 2 on the bottom. This one's pretty much the same. You would start by putting it over 1, but since it's an even, I'm going to go ahead and just show you the answer. That's what you guys should be ending up with on this particular problem. All right, now we move on to a division problem. With division, you do same, change, flip. And after that, it's just like the multiplication where you're going to factor and cancel. So the top doesn't factor, x minus 8 doesn't factor, and 1 doesn't factor, but this one down here does. I can take out a 6x squared out of this expression. If I divide this by 6x squared, I'm left with x. If I divide this by 6x squared, I'm left with minus 4, and the 6x squareds go away. Nothing else reduces, and that's my final answer. So the only difference for division is same, change, flip. There's another one for you to practice if you're interested, and the answer would be 1 over n plus 9 if you're interested. Let's go ahead and take a look at 11. Now we move into addition. So the first type of question that you can expect to see is maybe where they have a common denominator already. When they have a common denominator, basically you're just going to take the numerators and put them together over one common denominator. And then you're going to combine your like terms. So v plus v is 2v, and negative 1 and negative 2 makes negative 3. And then we leave it as this. It's possible you may need to reduce. So if you don't see this, it's going to be a multiple choice test once again. So if you don't see this in your answer choices, maybe what you need to do is reduce. So what I would do if I didn't see that in the answer choices is I would go through and I'd factor out what these have in common. Both of them could be divided by 4v, and that would leave me with v plus 5, but as you can see, nothing reduces. So this is probably what you would see in the answer choices. But technically, they could write it like this also. There's another addition one, but this one I will do for you guys. It's because this one has unlike denominators. Well, I'll do this one because 12 is just another unlike denominator problem, so I'll do 13. That's fine, yeah. All right, so when they don't have the same denominator, if you can, factor the denominators first. So on the bottom here, I can take out a 2n. I'm seeing that I don't really need this 3 here. These can reduce out, so might as well do that. That's irregular, though. That's not normally what ends up happening, but I'm going to do that just because it makes the problem a little bit easier. But you could actually just leave the 3 in there and get the same answer at the end anyway. But anyway, let's go ahead and continue. So now what we want to do is we want to get these denominators to match. So as you can see, I need a 2 over here. Whatever you do the bottom, you do the top. And I also need a 2n minus 5. Once again, whatever you do to the bottom, do to the top. So that's what you do whenever you don't have a common denominator. You factor and then you match the pieces as much as you can. So now I've got this. Here I'm going to go ahead and do 2 times 1 is 2, and then I'm going to distribute that into the parentheses. Now that they have a common denominator, I can go ahead and do what I did on the last problem, basically just combine these two things together. N and 4n makes 5n, 2 and negative 10 makes negative 8, and the bottom is already factored, and the top can't be factored and nothing reduces, so that's the only possible answer we should see. So number 12 is another example of an unlike denominator if you're interested. 14 and 15. So I'll do 15. 14 is same thing, not a common denominator, but this time it's subtraction. Same thing with 15. So for 15, I'll show you how to handle subtraction. So in this case, I can't factor the denominators, so they are what they are, but we still need to match them. So on this side, I need to put a 3b plus 1. And on this side, I need to put a b plus 2. That way they both have the same denominator. Okay. So now on the top, I'm going to distribute this 2 in to get 2b plus 4. And then here we're going to distribute this in to get 9b squared. Oh, I got a mistake here. That's a minus. That was the whole point of this problem. 9b squared plus 3b. Okay, now here's where the difference comes in. We're going to put these together into one fraction. But as I do it, this negative is going to be subtracting both of those terms on the top right expression. So now they both will change their signs. So that's the difference right there when it comes to subtraction, is before you start combining the numerators, distribute the minus into that top right polynomial. So now if I were to put this in descending order, I would put the negative 9b squared first. I would put 2b with 3b together to make negative b, and then 4 would come last. And in the bottom, I would have this. Technically, we would want to see if this can be factored. But honestly, I wouldn't even try it. I would look at my answer choices first and see if that answer was there somewhere. And if it was, then I would know I'm good. Most of the time, when you have a problem with not like denominators and you have to make them the same, they're not going to be reducible at the end. And sure enough, there it is. That's the answer. They've got the terms in a little bit of a different order than me, but it's the same thing. So we don't want to waste our time in factor if we don't need to. So always look at your answer choices first before you reduce. Anyway, going back to number 14, that's what you would have gotten for 14. And I did 13, and here's 12. I forgot to give you guys the answer for that one as well. So let's jump it up to our next one now, 16. Or no, I was going to do the odd ones, right? So 17. Okay, so this is what we call a complex fraction. It's when you have a fraction inside of a fraction. We have two little miniature fractions inside of one giant fraction. Okay, so what we do is we want to get rid of the denominators of the little fractions. So in this case, I don't like this little x here. The way we're going to get rid of that is by multiplying this fraction on the bottom by x over 1, and they cancel. But whatever I do to the bottom of this big fraction, I have to do the top of this big fraction. So I have to also multiply the top fraction by x over 1, which also cancels. That's really convenient. All I'm left with then on the top is 2, and on the bottom x minus 2, and I'm done. They're not often that easy, but that one turned out to be pretty chill. Sometimes you have more than one type of denominator, so you have to do it twice. If you guys remember those from class. Number 16 looks like this. So in this case, you have to multiply the top and bottom by x over 1 and also 9 over 1. But in any event, you would end up with that if you're interested in doing that particular even problem. Here's another one. This one's a little bit more complicated because it has 3 fractions in it. So we have 3 little fractions inside of one big giant fraction. In this case, we want to multiply everything by each of the little denominators to clear them out. So the first thing I'll do is I think I'll go ahead and get rid of the, let's get rid of the a minus 2 first. Why not? So I got to multiply this fraction by a minus 2, canceling those out. I've got to multiply this fraction by a minus 2, and I've got to multiply this one by a minus 2 just to keep everything balanced. So now, what do I have as a result of that? Here, I think I'm going to not multiply those together yet. Let's leave them separate. Let's put them next to each other over 16. So a times a minus 2, and 1 times 16 is 16. Plus, here, everything canceled out, so we have a squared over 1, which is just a squared. That was the point of multiplying by a minus 2, is to make that not a fraction anymore. Here, once again, I don't think I'm going to multiply yet. I'm just going to put them next to each other, and then a squared. The reason why I'm doing that is because if we multiply, we might end up not being able to reduce as easily. So I want to wait on that a little bit. The next thing I'm going to do is I want to get rid of, let's say, the 16. So now I'm going to multiply this by 16, so these cancel. But if I multiply that by 16, I've got to multiply this by 16, and I've got to multiply this by 16. So now, here, what I'm left with is a minus 2 times a, and that's it, because that's all that's left, plus 16a squared over 16 times 4 is going to be 64, a minus 2 over a squared. So I've gotten rid of 2 of the fractions. Now I have one more fraction to get rid of, and that's the one on the bottom here. So now I'm going to multiply everything by a squared to cancel that out. And what I have as a result of that is a squared times a is a cubed. All right. And at this point, all the fractions are gone, but we do want to simplify it as much as possible. So at this point now, I don't see anything's going to cancel out very easily. We can't get rid of the a minus 2's because I would have to have an a minus 2 over here also to do that. So what I'm going to do is I'm going to go ahead and distribute first, and that's going to be a to the 4 minus a cubed. I don't want to multiply the bottoms yet. Once again, that one I just want to leave. It's nice and simple. But on the top, by doing that, I can see now that I can combine this a to the 4th with that 16 to the a to the 4th. So that's going to give me 17 a to the 4th minus a cubed over 64 a minus 2. So at this point, we could factor out the top, but at this point, I would probably just stop and kind of look at the answer and see, do I need to go further? Because I don't want to reduce if I don't have to. Okay, so I see 17a to the 4th minus, should have had a 2 there. Wonder what I did wrong. And also on the bottom, you have 64 minus 128. So they distributed this to get that bottom there. But I'm kind of curious what I did wrong, so I want to back up a little bit. And let's see why they had a 2 and I did not. Oh, it's right here. When I distribute this, and that should have been 2a to the third. I guess I just missed that step somehow. But anyway, there it is. Good to go. All right. So if you want to see how to do number 18, or if you want to see the answer anyway, that's what you should end up with there. 18 should be a little bit easier than the one I just did. All right, let's take a look at number 21. And 21 and number 20, we're solving equations. So first thing when you're solving equations is, hold on. Okay, so this is solving equations. When you're solving equations, we want to get rid of the denominators. So let's do that. So what we're going to do is we're going to multiply the numerators by each one of these denominators here. So let's go ahead and start off by multiplying everything by n squared. So the n squareds here go away, the n squareds here go away, and here n squared over n can reduce. So I'm left with n over 3 here plus 2 equals 1. And then we just repeat that process to get rid of that final denominator there, which is the 3. So times 3, times 3, times 3. So here these cancel, leaving me with n. Nothing cancels here, so then I'm left with 6 equals 3. And subtraction gives us our answer, which is -3. And you always want to make sure at the end that your answer does not make the bottoms equal 0. So if you were to plug in -3 here, you would get -9, so that's okay. And if you were to plug in -3 here, you get +9, and that's okay. So long as your answer doesn't make the denominators of the original problem come out to be 0, then you got a good answer. So that's an example with monomials in it. Let's take a look at some examples with some polynomials in it. So in this case, when you have polynomials, what you want to do, of course, is factor first. So if you factor this one here using the box method, you would end up with -4 and +3. After that, it's pretty much just like the last problem we did. We want to multiply everything by the denominators to clear them out. So let's multiply everything by n minus 4 first. So those go away. Here, nothing goes away, but on this one, those go away. So now I'm left with the following. Okay, now we're going to get rid of the n minus 3 by multiplying that. So, not n minus 3, n plus 3. Okay, so that goes away and that goes away. That goes away, that goes away. And so now I'm left here with just a 2. Here I'm left with the 5 times n minus 4. And here I'm left with 1 times n plus 3. And then we're going to go ahead and just solve what we have left here using some basic algebra. So distribution. Combining like terms. Moving the ends onto one side. And so on. If I add 18 to both sides, I will get 21. And then we divide by 4. And the only thing that would end up making these denominators equal 0 would be -3 or +4. And my answer is neither one of those excluded values. So therefore, my answer is correct and a good solution. All right. I skipped this one, but I can show you guys the answer if you're interested. Let's see here. That was number 22. You should end up with 2/3. Okay. let's do another one here. All right. So let's see what happens here at number 25. Same process here. We're going to want to multiply everything by the denominators. In this case, I don't need to factor the denominators because they don't factor. But I will put this in parentheses as I multiply my v minus 4 there. V minus 4 also going to go times that one and also times that one. So for this fraction, they go away. And for this fraction, they go away. So now we're just left with that there, minus, nothing cancels here, so that's going to stay just the way it is. And over here we're just left with 1. For this one here we have v squared minus v minus 2. Distributing the negative 1, we get this. Okay, now this is a problem where we have a v squared and a v. Okay. Whenever you have squares and non-squares, that's a quadratic. And so what you need to do is you need to combine all your like terms and move everything to one side so it equals 0. So let's do that. First of all, I'll move the 1 over here so I get 0 on this side, leaving me with 3 when I combine that number with that number. And also I can combine these two v's together. Negative v and negative v makes negative 2v. I'll just bring down my v squared. And then this negative 2 and looks like a positive 3 there should make a positive 1. At that point, how you're going to solve these is using factoring. So if you factor this using the box method, I'm not going to show my work for that. I'm just going to go ahead and jump to the answer here. This is what you'd get. And you'd set each piece equal to 0, and you'd solve. Since they're the same, they're both going to give you the same answer. So we end up with just one answer here. It's v equals 1. And neither one of those answers make the denominator 0. So those are not excluded values, and therefore those are good solutions. Okay, so the big takeaway from this one is that when you have a square and non-squares, you need to move everything to one side and combine your like terms so you can factor it and use the zero product property. All right, 27. All right, so now we're moving into the graphing thing. So for these ones, we have a lot of work to do, as you guys know. The first thing that you're going to be asked to do on your test with these guys is you're going to be asked to determine the end behavior. End behavior is we want to find out what's happening at the extreme right of this function, and we also want to determine what's happening at the extreme left of this function. And what we've discussed is that the limit of this function at infinity or at negative infinity is really determined by the powers of the greatest on the numerator and denominator. So x over negative x, x over negative x. Actually, I don't like how I'm writing that. Let me back up a little bit. The limit of my function would be the same limit as just taking those, because those are the ones that really determine the outcome. Now, before we take the limit, we also want to reduce. That's negative 1. And what we talked about in class is anytime this is just a number, that's the answer. That's what the graph does at the extreme right and left, is it just goes to negative 1. And what that tells you is that your horizontal asymptote is y equals negative 1. So you'll be asked to, this will actually count for 2 point values, so to speak, on the test. This counts as 1, telling me what the end behavior is. Really, you could show all this work, I'll still give you full credit, but this is really good enough. You could just do it all mentally. It's not that challenging, actually. This would be the answer to the end behavior. this would be the answer to what is the asymptote. And they are the same thing pretty much because they go together. The next thing that you're going to be asked to do is you'll be asked to find your y-intercept. So to find your y-intercept, you plug 0 in the top and bottom. If I do that, you get 4 over 2 because these just go away. And that reduces to 2. So there's my y-intercept. The next thing we're going to do is we're going to factor the polynomial. Now, you don't get points for factoring that, but it's something you have to do to continue. Because actually, the next thing you want to do is you want to find the x-intercepts. And you can't do that until you factor it. Now, in this case, neither one of these are factorable, so that we can actually skip the factoring step. I guess technically, for the bottom one there, we could take out a -1. It's not necessary. It doesn't really change anything, but there you have it. But yeah, factoring is usually what you do, but in this case, it's not necessary. So next thing we got to do is find our x-intercepts. That's where you take the, or actually it's holes. You look for holes. Holes are when you have a factor on the top and bottom that are the same, and we don't have that here, so there are no holes. Then we go into finding our x-intercepts. X-intercepts are where you find the values of x that make the top equal 0. And the values of x that will do that are -4. There's only one. That's my x-intercept. Then we look for our vertical asymptotes. Vertical asymptotes are those values of x that make the bottom equal 0. And so for that, we get 2. Okay, now I'm not labeling what these are. I'm just saying it. But let's go ahead and graph it now. First of all, we saw that we had a horizontal asymptote at -1. So I'm going to draw a horizontal line at -1. That's what we got from step 2. From step 3, we saw that our y-intercept was 2. From step 4, we saw that there were no holes, so we'll skip that. From step 5, we saw that there is a x-intercept at -4, which means it touches the x-axis at -4. And then finally at number 6, we saw that there was a vertical asymptote at 2. So I'll draw a vertical asymptote at 2. And so what we're looking for is we're looking for some curves that will abide by all of these parameters that we have up here. So at the ends, it has to get really close to this asymptote, okay? And it also has to hit this dot and this dot. And it also has to get really close to this asymptote. So the way that's going to work is if I start close to the asymptote, follow through, hit that point, and swing back up. And that's what that curve would look like. Now to find the other side, because there is a graph over here, we just need to find out what it is. We don't have any data here, but we don't need, actually it's our lack of data that tells us what it is. There's 2 possibilities for this, but one of them actually isn't a possibility. Here's one possibility, and here's another possibility. Because it has to squish up against these asymptotes. So it's got to be like that or like that. Now the reason we know it's not the top is because it's not allowed to touch the x-axis because we only have one x-intercept right here, -4. We can't have another x-intercept, so it can't be this top one. Too far. So that means it has to be the one on the bottom. So a lot of times you can determine where the curve goes because it shouldn't be touching the x-axis anymore. Okay, so there's that final graph for that one. Let's do one more with you guys here. Number 20, actually 28. I'm going to do 2 more with you. I'm going to do 28 and 29. All right. So, number 28, end behavior. The limit as x goes to infinity, and the limit as x goes to the -infinity. What's happening at the extreme left and right of this function, in other words? I think I'm going to show my work a little bit differently this time. So For this one, I'm going to show my work on the side, and I'll just put my final answer right next to it. So the limit of this function at infinity will be the same thing as the limit of the first two terms there at infinity. And then we're going to reduce that. And another way we could write this, just so it looks maybe a little bit more familiar, is like this. Now this expression here is in the form ax to the nth power. When it's in that form, it's not going to have a horizontal asymptote. Instead, the ends of the function are going to either go up or down. They're not going to go flat against a horizontal asymptote. So, I gave you guys a chart for this. And in the chart, we have to determine whether the a is positive or negative, and we also have to determine whether the n is even or odd. Now in this case, my a is negative and my n is odd. And when that happens, the ends of our graph looks like this, which means that as I go to the right, the graph goes down to negative infinity. And as I go to the left, the graph goes up to positive infinity. Okay? Another way you guys can do this instead of using the chart if you want is you could just plug in infinity. If you plugged in infinity here, because that's what this means, x is going to infinity, so just plug it in. Negative 1/4 times infinity, well, what would that be? Well, no matter what you multiply infinity by, it's going to be infinity, but since this is negative, it's going to make it negative infinity. So as we go to the right, the function goes down. So the arrow would look like that on our graph on the right side. So the answer to that one is negative infinity. Now let's do this one. What about the limit as x goes to negative infinity? Well, we looked at the chart already, and we said as we go to the left, the function goes up. So in that case, as we go to the left, it goes up. So for the first one, as we go to the right, it goes down. And as we go to the left, it goes up. So on the left side of my graph, I've got an upward facing arrow, and on the right side of my graph, I've got a downwards facing arrow. Okay, and as I mentioned before, when that happens, that means we have no horizontal asymptotes. Number 3. You're supposed to factor it at this point. It's a lot of factoring to do here, it looks like. So on the top, I can take out an x. Oh wait, I forgot to do my y-intercept, didn't I? Before I factor, let's do our y-intercept. That was the next thing. So if I plug in 0 on the top, I end up with 0. And on the bottom, I end up with 8. And when you have 0 over 8, that's just 0. So my y-intercept is 0. Now we move on to the factoring. On the top, I could take out an x, which would leave me with the following. And then for these polynomials on the top and bottom, we would go ahead and use the box method to factor them. Okay, the next thing we do is we look for holes. On this particular problem, there are no holes because there's no factors on the top and bottom that match. Next, we look for the x-intercepts. Those are the that's the terms that make 0 on the top. So 0, -3, and +4 are all the values that will make the factors 0 on the top. So 0, -3, and +4. Number 6. Now we look for the vertical asymptotes. Those are the values that make the bottom 0, so that would be 2 and -1. Okay, so we're ready to start graphing this. All right, so step 1 is not something we graph, but step 2 is, but we can't because we don't have one. Step 3 is a y-intercept, so it touches the y-axis at y equals 0. Step 4, holes, none of those. Step 5, we have x-intercepts at 0, which we already have for the y-intercept, -3, and +4. Number 6 tells us our vertical asymptote, so I have a vertical asymptote at 2 and at -1. We also know our end behavior. Actually, I forgot. We do need to worry about number 1. That tells us our end behavior. As we mentioned before, as we go to the right, our graph goes down. So on the right side of my graph, it looks like that. And as we go to the left, it goes up. So on the left side of my graph, it goes up. So that's what the ends of my function look like. Now it's got to go. Let's start over here on the right side. It's got to hit that dot and it's got to hug up against the asymptote. There's only one way that's going to happen. That's if it looks something like that. And on the other side, the opposite happens. It's got to hit that dot and hug up against the asymptote, so it's going to look like that. Now we got to figure out what's going on here in the middle. There are two possibilities. It could be going like this, or it could be going like this. And so to know what we need to do, basically we need to pick a test point. Now, sometimes you have to pick fractions, like if that's all you have to choose from, but I don't have to pick a fraction. I've got one point here that I can pick. You don't want to pick a root, because if you plug that in, you're just going to get 0. That's what roots do. But we want to pick something that's not a root. And that way, if I end up with a positive, then I know it's above at that point. If I end up with a negative, then it's below at that point. And that helps me get more information to graph it. So let's plug in 1. If I plug in 1 here, I get a positive. If I plug in 1 here, I get a positive. If I plug in 1 here, I get a negative. This is a negative, -4. But if I plug in positive 1 here, I get negative. If I plug in 1 here, I get positive. So on the top, a positive times a negative is negative. And on the bottom, 2 negatives and a positive makes a positive. If you divide a negative by a positive, you get a negative. So that means that at x equals 1, the y value comes out negative. So it's going to be somewhere down here. And so now I know my graph has to look like this. And there it is. All right, one more. 29. All right. Let's find out what happens at the far right of our function and what happens at the far left of our function. Let's start off with the far right. So this limit will be the same thing as this limit, where we just look at the first terms. Now I mentioned to you guys that anytime you have an x in the denominator but just a number on the top, that's always going to come out to be 0. And when that happens, the other one's going to be 0 also. And anytime you get a number here, that's basically a horizontal asymptote. That means no matter how far you go to the right or how far you go to the left, the graph goes towards 0, a definite flat horizontal line of y equals 0. So my horizontal asymptote in this case would be y equals 0. All right, C. Next, we try to find our y-intercept. So I'd plug in 0 to the top, which you can't do. And then I'd plug in 0 to the bottom, which is this. So I end up with -½ as my y-intercept. For D, we got to factor it to get our answer. We're looking for holes and x-intercepts and stuff. Well, there's not much I could do here. I could take out a 2. But that's not going to do much good for me here. So let's go back. Are there any holes? The answer is, once again, no holes. Next, we have E. What are the x-intercepts? That's when the top equals 0. Well, you can't say that 1 equals 0. That doesn't make sense. So there are no x-intercepts. And by the way, anytime your horizontal asymptote is y equals 0, well, I guess that's not true. You can still have horizontal asymptotes. But it's possible. It's common for it not to have x-intercepts when that's what your horizontal asymptote is. But it's still possible, technically. Anyway, let's continue. Vertical asymptotes is next. That's where the bottom equals 0, and that's what this number is here. So x minus 1 equals 0. There's my vertical asymptote. So we're ready to graph. So this graph has a horizontal asymptote at y equals 0, the x-axis there. That takes care of this. C, we have a y-intercept at -½, so if this is 1, -½ would be like right about there. D, there's no holes. E, there's no x-intercepts. And F, we have a vertical asymptote at x equals 1. Okay, so let's start off on this side over here. It's got to squish up against this asymptote, and it has to hit that dot. There's only one way that's going to happen. So if it does this. Now on the other side, we have no idea. It could go like this, or it could go like this, and in neither case is it hitting the x-axis, so we can't use that little rule we used back on number 25, where it hit the x-axis. So in this case, we actually just got to do a test point to get an answer here. So I'm going to pick any point over here on this side of the graph. If I end up with a positive, then I know it's up here. If I end up with a negative, then I know it's down here. So I'll plug in 2. If I plug in 2, we have a positive on the top because it's just a positive 1. This 2 is a positive. And then if I plug in 2 here, that's a positive. It's all positive, so it comes out positive, and my graph would have to look something like that. Oakley dokley. So that kind of sums it up there, guys. That's the end. Hope that was helpful to you. We'll see you guys in class tomorrow.